Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Nik Ilhami binti Ibrisam and my metric number is P20EC3013. So for this project Sarjana Muda session 2023-2024 semester 2, my research-based project is under the title of Comparison of Machine Learning Algorithm for Selecting Event Sequence Test Cases, and my supervisor is Dr. Johanna binti Ahmad. So under this presentation, I will present 5 topics, which is introduction, literature review, research methodology, research design and implementation, and also result analysis and discussion. Introduction and problem background. Test case selection, or TCS, is a reduction technique for test case suites in regression testing during software testing process to find defects and flaws in the system. However, redundancy is a challenge in TCS, as same test cases might be selected to retest that may reduce the efficiency of TCS. And this study compared the effectiveness of existing TCS machine learning algorithms and event sequence-based test cases is the focus in the study of comparing machine learning algorithms in performing TCS. So the research question would be, number 1, what ML techniques are used for test case selections? Number 2 is how to evaluate the effectiveness of TCS techniques implemented with ML algorithms. For the research objectives, we have 3, which is the first one is to identify the most appropriate machine learning algorithm for selecting event sequence test cases, and number 2 is to enhance the existing machine learning technique for selecting event sequence test cases, and number 3 is to assess the effectiveness of selected machine learning algorithm. The scope of this research will focus on 2 scopes, which is to evaluate and compare the WAS and ESPS, which is an algorithm implemented in TCS in its accuracy in selecting appropriate event sequence test cases. And number 2 is the effectiveness of this algorithm will be evaluated based on their ability to calculate the possibility of every test to be a failure and enhance the test coverage. The research contribution will be 3 things, which is the first one is to identify the most appropriate machine learning algorithm for selecting event sequence test cases, and number 2 is to enhance existing machine learning technique for selecting event sequence test cases, leveraging the strengths of different algorithms and integrating them into a unified approach that maximizes fault detection rates. Number 3 is to evaluate the effectiveness of proposed machine learning algorithm for selecting event sequence test cases using failure detection ratio and test selection ratio. For the literature review, we will focus on 4 main factors, which is first we're going to start with software testing. Software testing is a process of validating and verifying that the software product meets the requirement of its stakeholder. And from the software testing, we will see the machine learning in software testing, and the disciplines of software testing has seen the emergence of machine learning techniques as potent tools, opening up new possibilities for improving test efficacy and efficiency. And next, we will see the test case selection and machine learning in test case selection. So, the description and the purpose of this literature review is to explore the present state of research in test case selection using ML algorithm, covering the strengths and limitations of existing methods as well as prospective future research directions. And from the literature review, we find that there are 6 techniques in anomaly detections in software testing, and among them is clustering using k-mean. And in 2017, CASMI has provided a conceptual framework regarding how to conduct regression testing, that is TCS, that lists the activities to be conducted. And this study looks into cluster sampling techniques, which are weighted attribute-based strategy WAS by Wang in 2012, and execution spectra-based sampling ESPS by Yan in 2010. And the evaluation metric used for both techniques are failure detection ratio and test selection ratio. But in this study, we only perform the first one, which is the failure detection ratio. So the existing ML techniques in TCS fall under 4 categories, which is the supervised learning, unsupervised learning, reinforced learning, and NLP, which is natural language processing. So under supervised learning, we have the techniques such as random forest, support vector machine, and for the unsupervised learning, which are the scope of our research, falls under the category of clustering technique, which is WAS and ESPS. So for the cluster sampling strategies, we introduced earlier, which is ESBS and WAS, are based on these two papers that title A Dynamic Task Cluster Sampling Strategy by Leveraging Execution Spectra Information by Yan in 2010 and Using Weighted Attributes to Improve Cluster Test Selection by Wang in 2012. So the datasets used in both programs are benchmark sources, which 5 of the 7 classic Siemens programs and also 3 open source programs, which is Flex, GREP and GZIP. So the difference is that the confidence calculation used in ESBS are performed by Stepman and using 7 equations, which is the confidence, suspicions as correct formula, and also for the WAS technique, the confidence calculation are performed by function weight, and the measurement methods used are jacket ranking metric. So why we're using ESBS and WAS? Because both of them are using the k-mean clustering ML algorithm by clustering the test cases using the Euclidean distance, and the difference is only the methods of confidence calculation using statement for ESBS, and for WAS are using function weight calculation. And for the expected result, our ESBS can get lower test selection ratio and higher failure detection ratio than other cluster sampling method, which is adaptive sampling and also one per cluster sampling. But for WAS, can get lower test selection ratio and higher failure detection ratio than ESBS and other cluster sampling. So for the evaluation model used are failure detection ratio and test selection ratio, and both formula are stated in ESBS and WAS are almost the same, which is the failure detection ratio is to find the percentage of failures found from the test case selection, and also for the test selection ratio is the percentage of tests selected. Moving on to the research methodology, there are 5 phases of research methodology, which starts with the phase 1 literature review. And the first step in doing this research is by conducting literature review based on related previous studies. For the second phase would be the problem formulation by using the identified research gap from the literature review to path the way for problem formulation in this study. And the third phase would be data collection and data pre-processing. And the goal of data collecting and pre-processing is to collect and analyze relevant information to answer the research questions or achieve the study's objectives. And the fourth phase would be experiment. The experiment involves running tests, clustering similar test cases using k-means, applying ESBS and WAS sampling strategies, selecting test cases, and evaluating effectiveness using failure detection ratio. And the last phase would be phase 5, which is result analysis and conclusion, where we are going to analyze both result of selected test cases and its evaluation metric. So for the dataset programs used in this program are 2 Java program, which is bank program and circular queue program, and its test cases consist of around 32 to 40 test cases, and it is both are event sequence based test cases. So for the research design and implementation, there are 6 steps, which is the first one is to running tests with mutation, number 2 is to perform k-mean clustering, number 3 is to perform the cluster sampling, number 1, which is ESBS, and the next step 4 is to perform the cluster sampling, number 2, which is WAS, and the 5th step will be perform test case selection, and the last step to evaluate ESBS and WAS using failure detection ratio. So the first step is to perform mutation testing using Jester and JUnit. So in this first phase of the project, testing for mutants is conducted using the JUnit and Jester frameworks. And mutation testing involves the generation of source code mutants that are then executed against test cases to determine how many of them detect the introduced faults. And the result from this phase will eventually provide a foundation for the clustering process in the subsequent phase. So to create a robust test testing, Jester is used for the creation and management of mutants, while JUnit is used for running the test cases. As you can see in the diagram of mutated code using Jester, there are 20 mutations performed, and these are the original code and the mutated code, which involve mutation operators such as changing from the plus to minus and also changing the return values. For the JUnit testing is performed in Eclipse IDE. For the k-mean clustering, will be performed to classify the test cases into 2 or above cluster, which is T and T prime, and the distance between the cluster will be calculated using Euclidean distance formula below. So the EI refers to where the function I is called in test T, and E prime I refers to where the function I is called in test T prime. So these are the example how the clustered data looks using K-mean. So next step will be the ESBS sampling strategy, which is to identify and prioritize potential bugs by iteratively selecting test cases that execute the highest number of suspicious statements, incrementing or decrementing confidence value based on test results. And initially, all statements are flagged as suspicious and confidence values are set to 0. As test cases are executed, passing tests increments the confidence values of the executed statements, while failing tests decrement them. And this dynamic adjustment helps re-evaluate and refine the list of suspicious statements continuously. So the process will terminate when no further test cases in a cluster execute suspicious statements, providing a final output of suspicious statements with confidence values to guide debugging efforts effectively. So for the WAS strategy, which is the upcoming phase of the experiment, involves implementing the WAS framework cluster sampling strategy, focusing on function confidence and weight calculations to identify and prioritize potential bugs. So there are 3 steps, which is first one is to function confidence calculation, which is all functions initially are flagged as suspicious and confidence values are updated based on test result, with passing tests increasing and failing tests decreasing confidence. So this is almost the same with the ESBS statement confidence calculation, but the difference is the ESBS focus the confidence calculation based on the statements performed in the test case, while WAS perform the functions confidence calculation, which is based on which functions are called in each test cases. So the next step will be the function weight calculation. So the function weight calculation uses the jacket similarity metric, and each function was assigned to a specific ranking metric of A and P, which is the function that are not executed and pass, A and F, function that are not executed and fail, AEP, the function that are executed and pass, and lastly AEF, which is the function that are executed and fail, comparing failing tests with those calling of functions to determine the probability of faults. And next step will be the new profile. The final step involves updating test case profile based on these weights, providing a targeted analysis that prioritizes test case for debugging, thereby enhancing the efficiency and accuracy of fault detection and correction. So the TCS process are based on both strategies. For the ESBS strategy, TCS prioritizes test case executing suspicious statements identified by ESBS and enhancing efficiency by concentrating on code areas most likely to contain bugs based on statement confidence value. For the WS strategy, TCS prioritizes test case following suspicious functions identified by WS, allowing for a broader analysis of potential systemic issues in code by focusing on functions implicated in multiple test failures. So for the failure detection ratio using in the evaluation metric, we are using the formula of failure detection ratio, which is the percentage failures found, where we're going to divide the found failure with the total number of failures and calculating its percentage. So this ratio provides a clear measure of the method's ability to identify failures within the system, reflecting its effectiveness in failure detection. And by using the failure detection ratio, the performance of WAS and ESBS can be quantitatively compared, ensuring a robust evaluation of each strategy's capability to enhance software reliability. So, mutation testing results using Chester and JUnit. So a total of 20 mutations were produced for 305 lines of code program bank, and the following 2 tables besides are fault metric tables that shows the result for each mutation. And nonetheless, not all mutation will be used for clustering and cluster sampling strategy due to time restrictions to perform the experiment, and the focus is on the sampling strategy and not the mutation testing. So from both metric tables, we only choose mutation number 3 from bank program and mutation number 1 from CQ program. So for the clustered test cases, from the result of pass and failure of each test cases based on the mutation testing, the clustering algorithm using K-mean calculation was performed. So for the bank program, we achieved 2 clusters after 2 iterations, and the total test case for cluster 1 is 7, and cluster 2 consists of 33 test cases. And for CQ program, after 3 iterations, we managed to get the 3 cluster, which is the cluster 1 consists of 8 test cases, cluster 2 consists of 17 test cases, and cluster 3 consists of 7 test cases. And then we perform the ESBS by statement confidence calculation, and these are the results for each cluster for its suspicious test case and suspicious statements. For example, for BAM program in cluster number 1, all statements executed in cluster 1 is suspicious, so all test cases in cluster 1 need to be retested. Meanwhile, for the CQ program, when we see in the cluster 1, only statement number 13, number 14, and number 15 that does not surpass CT value of 2, and the remaining test cases are not a suspicious test cases since they did not cause statement 13, 14, and 15. Next, we will see the WS, which is the suspicious function calculation was performed for each cluster to determine the sequence of most suspicious test case ascendingly. So this sequence will be used to determine the ranking matrix since it's a summation of the test case ranking matrix. Compared to ESBS, we did not perform all the confidence calculation, but we will stop, or the process will terminate when it's already achieve the confidence threshold. But difference for the WS, we perform until we can see the ranking orders for each test cases in every cluster. So from for bank program, as we can see from the cluster number 1, we have the 4 functions which is E1 is deposit, E2 is transfer, E3 is withdraw and inquiry, and these are the ranking metrics and also its functions weight for each functions in every cluster. For bank program and also CQ program, we have the 3 functions which is front, add, and remove. So after we manage to find the function weight and also its ranking metric, so we are going to see which functions that has the higher function weight value. So the higher the function weight value, the higher number of failed tests called the function. So the function weight for each function will be used to calculate the new profile for each test cases. And based on this profile, the test case with highest function weight will be selected to be retested since they are considered as test case with high failure probability profile. So the star symbol in both table indicates the highest function weight value. So for bank program, we have the E1, which is the function of deposit as the highest function weight, which is also means the highest probability for the failure test case base is at the function deposit. So the new profile is generated by using each function's weight to replace the values in the original profile. So they involve recalculating the profile of each test case based on the updated confidence values of the functions they call. And the calculation of function weights for the new profile involves multiplying the number of times a function is called by its respective function weight, and we can get the new profile. So for example, in this, I think is the bank program, we have 4 functions which is deposit, transfer, withdraw, inquiry. For the test case 1 in cluster 1, the function deposit is called 10 times, while the function transfer is called 1 time, and inquiry is also called 1 time. So we multiply with its function weights and we can get the new profile. So with the result of suspicious statements from each cluster, then the TCS can be performed. So for this first sampling strategy, which is ESBS, we conclude that from circular queue program, out of 3 cluster, only 20 from 32 test cases are selected, and the suspicious statements is 12 statements, and the number of selected test cases is 20. and we got the percentage of selected test cases is 62.50%. While for the bank program, only 8 from 40 test cases are selected, with also the same 12 statements that are suspicious, and the selected test cases percentage is only 20%. And then for the WAS strategy, the TCS result is as below, which is for the circular queue program, only 28 from 32 test cases that are selected, and the suspicious function is function number 3, which is remove, and the average weight for the function number 3 is 5.415, and the percentage of selected test cases is only at 87.50%. And for the bank program, only 14 from 40 test cases are selected, and the suspicious function is the function number 1, which is deposit, and the average weight for those function is 9.944, and the percentage of selected test cases is 35%. So based on this TCS result, we will evaluate using the failure detection ratio. So for program circular queue with the clustering technique of ESBS, the total test case is 32, and the total failure in that program is 13 test cases, and the total of failure found is only 10 test cases. So that means the failure detection ratio is only at 76.92%. Meanwhile, for WAS technique, the total of failure is 13, and the total of failure found is also 13. So thus the result of failure detection ratio is at 100%. And for the bank program ESBS, the total of failure is 14 out of total test cases is 40, and the total of failure found by the ESBS technique is only 8. Thus, the failure detection ratio is at 57.14%. Meanwhile, for WAS program, it finds all the failures, which is 14 in the bank program. So the failure detection ratio is at 100%. So the effectiveness comparison, the WAS sampling strategy demonstrated superior effectiveness in failure detection compared to the ESBS method, with WAS achieving a 100% failure detection ratio in both circular queue and bank programs, while ESBS only achieved 76.92% and 57.14% respectively. So the program-specific result for the circular queue program ESBS only detected 13 out of 13 failures, whereas WAS detected all 13 failures. Similarly, in the bank program, ESBS detected 8 out of 14 failures, whereas WAS detected all 14 failures. So the conclusion is the WAS methodology proved to be significantly more reliable and thorough in detecting failures in software testing than the ESBS method, highlighting its effectiveness in ensuring software reliability. So the achievement of this project objectives, there are 3 points, which is the algorithm evaluation. So the study identified that the WAS technique consistently outperforms the ESBS technique in failure detection ratio for even sequence test cases, achieving a 100% failure detection ratio in both the circular queue and bank programs compared to only 76.92% and 57.40% for ESBS respectively. And next will be the improvement of implementation. The research proposed and implemented improvements in function confidence calculation and profile updating process, introducing a constant confidence ratio at CT value number 2 to ensure fair comparison and enhancing the performance of the WAS technique. And for the efficacy assessment, the study proved the superiority of the WAS technique over ESBS in identifying and prioritizing event sequence test cases, underlining WAS potentials to improve the reliability and efficiency of test case selection process in software development. And the suggestion for improvement and future work is that future research should evaluate machine learning algorithm using a larger and more diverse sets of programs to enhance precision and generalizability, eliminating bias from small data sets and provides more realistic assessments. And the transition from the outdated Jester tool to state-of-the-art mutation testing tools like PEAT, which offer advanced features, usability, robustness, and efficiency, thereby improving the reliability of mutation testing processes. And to incorporate advanced machine learning techniques such as deep learning and reinforcement learning into test case selection focused on event sequence to further enhance the accuracy and efficiency of the TCS process, leveraging this method's ability to learn and adapt to unique software systems characteristics. So I guess that's all from me. Thank you for watching.